This week, we look at the performing arts, opera, dance, and fireworks. Let the celebration begin. Did you know that when you vibrate your vocal cords, you're actually playing the world's oldest musical instrument? In the beginning, singing was a means of imitating nature's sounds, but it soon became a means of expression and creation. Mastering it is a highly complex process. The human voice in music is, in a way, the most complete of instruments. Acquiring a good singing voice, however, requires years of training. The vocal mechanism consists of three elements: a blower provided by the lungs, a vibrator consisting of the vocal folds, and a resonator made up of the pharynx, the nasal cavities, and the mouth. In singing, the airstream from the lungs strikes the vocal folds, two membranous bands located in the larynx, and makes them vibrate. At their extremities, the vocal folds are connected to mobile cartilages. The cartilages allow the vocal folds to move apart or come together, grow thicker or thinner, and increase or decrease their tension. The thinner and tauter the vocal folds are, the faster they vibrate. They let the air out in puffs that flow in more or less rapid succession. The closer these puffs are, the higher the sound produced. Upon emerging from the larynx, the sound goes through the various resonant cavities. Depending on its path and the shape the oral cavity takes, the sound changes. This is where it acquires a tone, that is, a specific color. For example, when you sing the vowel ah, the sound comes solely out of the mouth. On the other hand, when producing the an vowel sound, the air comes out of both the nasal cavity and the mouth. And the production of vowels like oo requires the elongation of the resonant cavity between the lips. While it is relatively easy to produce vowels in singing, the same does not hold for consonants. Indeed, the production of consonants occurs as a result of a momentary obstruction of the vocal tract between the larynx and the mouth. The closure of the vocal tract interrupts the flow of air. This entails brief silences that break the continuity of the melodic line. To reduce these silences, the singer articulates the consonants softly. He thus limits their duration and the degree of occlusion of the vocal tract needed to produce them. Such tactics, however, make it difficult to clearly hear the text being sung. That is why the languages that best lend themselves to song are the ones that contain lots of vowels, such as Latin or Italian. In the art of classical singing, there are 6 main vocal categories. From high to low, females' voices are classified as soprano, mezzo-soprano, and contralto. In male singers, there are tenor, baritone, and bass voices. It is mainly the size of the vocal folds that determines a person's register. Men, for instance, have a bigger larynx and therefore longer and wider vocal folds than women. In men and women alike, There are basically two modes of sound production. In producing bass sounds, the larynx descends toward the rib cage. In singing, the vibration of the vocal folds is transmitted to the skeleton. The larynx therefore communicates its vibrational energy to the thoracic wall, and the singer has the feeling his voice is resonating in his chest. However, when producing high sounds, the larynx is elevated relative to its rest position. The vibrational energy is then felt in the skull and facial bones, and the singer has the impression that his voice is echoing in his head. It is these inner resonances that enable a singer to pitch his voice. When a person sings a note, his voice not only produces the fundamental sound of that note, but also a whole series of secondary, higher sounds called harmonics. If his voice is well positioned, the highest harmonics will be strengthened. This reinforcement allows a singer to be clearly heard over the instruments, which usually generate harmonics of a lower frequency. In addition, he must try and strike a balance between the quality of the sound and the clarity of the text he is singing.
The art of dancing is just as demanding as singing. Ritual dance has already existed in the Paleolithic age, 12,000 years ago. Dancing is learning how to compose with the laws of biology and physics.
More than a purely aesthetic art, dance is a means of expressing emotions and ideas. However, dance movements are governed by the principles of a science, biomechanics. Dance is a combination of dynamic movements and static positions. To execute this body language as a whole, above all, the dancer must know how to control his balance. A dancer is in balance when his center of gravity is above his support base. The support base corresponds to the surface on which the body rests and is defined by the position of the feet on the ground. As for the center of gravity, it is an imaginary point about which the weight of the body is symmetrically distributed. When a dancer is standing, arms at his sides, his center of gravity is situated at the level of his pelvis. However, the location of that point varies according to the position of the body. For instance, when the dancer lifts his arms, his center of gravity rises, his balance becomes precarious. Indeed, when his center of gravity is higher, movements, such as leaning forward, make him leave his support base more easily. For instance, a tall dancer whose center of gravity is higher than a shorter dancer's is easily set off balance. The dimension of the support base also affects the stability of the equilibrium. For instance, when he has both feet firmly on the ground, the dancer has a broad support base which ensures him a stable balance. Conversely, the balance of a dancer performing an attitude en pointe is much more unstable since her support base is smaller. As soon as the dancer's center of gravity falls outside of her support base, balance is lost. Jumps are important elements in dance. The grand jeté, a big leap forward, is especially spectacular because it gives the impression that the dancer stops in midair. Two factors account for that illusion. First, while the dancer's horizontal speed remains constant throughout the jump, his vertical speed varies due to the effect of gravity. The dancer's body rises quickly at the beginning of the jump, then its speed gradually slows down to become nil at the height of the jump. Then it increases as the body descends and until it lands. As a result, for about half the total time of the jump, the dancer's body is located in the upper part of its trajectory. A second factor reinforces the illusion that the dancer hovers in midair during a grand jeté. In this jump, as in any other, the center of gravity always follows a parabolic curve. Nothing can alter that trajectory, since it is determined by the Earth's attraction. However, in a grand jeté, the dancer spreads his arms and legs at the top of the leap. This raises his center of gravity from the abdominal region to the level of the stomach. Elevating the center of gravity in this way enables the body to effect a horizontal movement for a brief moment. Its trajectory then seems to flatten. The fact that the dancer does the splits at the height of the jump enhances that illusion of suspension. To perform such sweeping movements as the splits, the dancer obviously has to be very supple. While suppleness improves with practice, some people are born naturally supple. In such persons, the tendons, ligaments, and tissues surrounding the muscular fibers contain a greater number of elastic fibers. These fibers consist of a protein, elastin, that enables the tissues to lengthen when stretched. A dancer's suppleness is in part developed at a very early age. That is when our bone structure is still largely made up of cartilage. It is therefore malleable, and through stretching exercises, the bones can be made to gradually take on the shape we want. Such changes to the bone structure of the body can be made as long as the ossification process is not completed. Ligaments and tendons also have their own adaptation mechanisms. When they are subjected to tension, for instance, the elastic fibers they consist of line up and come closer together, allowing them to lengthen. Becoming a dancer involves lengthy and exacting training. But in every performance, the dancer has to learn how to go beyond technique and give expression to the soul.
During the course of history, like everything else, the performing arts were influenced by technological change. Pyrotechnics is a good example. It all began in China around the 8th century with an invention that was to make quite an impact: black powder. Ever since, no celebration is truly complete without fireworks.
5, 4, 3, 2, 1.
A hiss, then, suddenly, a bouquet of multicolored streamers and a huge umbrella appear, producing a shower of brilliant, fleeting stars. To create such works of art, the pyrotechnist has an impressive variety of technical means at his disposal. However, we are only just beginning to understand the physical and chemical phenomena that produce the dazzling effects of fireworks. There are countless types of pyrotechnical devices. Some light displays are exploded at ground level, producing cascades and fountains. Most soar high in the sky, such as the comet, which streaks upwards, leaving a luminous trail behind it. Then there is the Roman candle that repeatedly fires various luminous compositions into the sky, and the multi-stage rocket that explodes in stages. The shapes and colors of fireworks mainly depend on the structure and chemical composition of the pyrotechnic devices used. For example, the Japanese bomb, which bursts in the shape of a chrysanthemum, is a spherical projectile consisting of 3 compartments. At the basis of the bomb is an explosive charge to project it into the sky. Near this first compartment, a slow combustion device is inserted. Its purpose is to delay the ignition of the 3rd compartment, which contains the compounds with the luminous effects. The delay prevents the bomb from firing before reaching the predetermined height. Like most fireworks, the Japanese bomb is projected by black powder. Black powder is a mixture of charcoal, sulfur, and potassium nitrate, more commonly known as saltpeter. When ignited, the mixture generates a sudden and considerable emission of gases. The gases are trapped at the bottom of a mortar, a sort of steel cannon buried in the sand, into which the bomb is placed. Since the combustion gases can only escape upwards, they eject the bomb from the mortar. Depending on the amount of black powder put into its base, the bomb can attain heights of 50 to 400 meters before exploding. The stars are contained in the head of the bomb. These little pellets are formed by the clumping of chemical compounds that give off a colored light when they burn. They are coated with black powder so they will ignite. In the chrysanthemum-type Japanese bomb, the stars are arranged in perfect symmetry inside a spherical shell, also filled with black powder. When the shell explodes, it projects a myriad of brilliant streamers of stars. Once lit, the stars become sources of iridescent colored light. For example, those composed of powdered aluminum or magnesium produce a white light. When this particular powder burns, it forms particles of metallic oxide that reach temperatures of 3,000 degrees Celsius. At these temperatures, the particles produce a white glow. Charcoal and iron particles, on the other hand, burn at less than 1,500 degrees Celsius. These stars produce golden sparks. The other colors fireworks can produce are the result of an atomic phenomenon. When an atom of sodium is heated, for example, the heat excites certain of the atom's electrons. They become highly energized. The moment these electrons return to their stable state, they release the surplus energy thus absorbed in the form of an orange-yellow light. Some combinations of atoms or molecules will also produce colors when going from a high energy level to a more stable state. This is the case of strontium compounds, which produce a red flame. Green colors are obtained with molecules containing barium. Blue is the most difficult color to produce. To date, copper salt compounds have been the ones to produce the best effects. The length of time a star burns is determined by the size of the small pellets containing the chemical compounds. Small particles produce short-burning stars, while large ones produce stars that burn longer, leaving long trails of light in their wake. Although short-lived, firework displays require meticulous preparation. First, the mortars are installed. Into each one, a bomb is placed. Then the fuse of each bomb is connected to an igniter. The igniter is in turn connected to a conductor wire hooked up to an electrical unit. On the evening of the display, the pyrotechnist ignites the projectiles from the firing console. In some cases, he adds choreography to his visual effects and makes a combination light-music display. Orchestrating musical firework displays is delicate work, but when successful, the result to the spectator's delight is pure magic.
From ancient Greece to our day, the performing arts serve the same purpose: to rise above the miseries of everyday existence and to celebrate life's mysteries.